Peace be upon you. Let's talk today about a very interesting topic. Why are the images on the left labeled as image A, image B, image C, and image D? The reason is that the image is pixelated. You can see the squares that are starting to appear. We call these squares pixelation because the image is beginning to pixelate. Why is this pixelation happening? Or why does the image look so large? Because the area is simple and the matrix size varies. Every image in the world consists of squares, and each square is called a pixel. The number of pixels in the image determines its resolution. I call each square a pixel. So the number of pixels present in the image determines what, for me, the resolution of images determines what this means. It means that this image has a number of pixels less than the image 5C, and C is less than B, and B is less than A. This means it has the largest number of pixels, as I mentioned, in the largest matrix size. So when I said that I have a matrix size of 512 by 512, this is an image. It consists of 512 pixels in a row and 512, making a total of 512 rows in 512, which I call the matrix size. So this single unit is called a pixel, and thus it has a pixel. What is it? It is indeed the elephant, which is the entire group. On the matrix, there is another size, which is your complete image. On the full matrix size, which is a complete row and a complete column. What does it give you? Well, when we come to import number B, we find here, for example, the possible matrix is essentially 64 by 64, meaning 64 rows and 64 columns. This 64 by 64 is the matrix. So when we come to optimize, the pixel size in the view field of 64 gives a pixel size of 3. So is pixel size 3 larger, or is pixel size 4 larger? Pixel size 3 is larger. Now in the case where P is greater than the pixel, it just commands. So the house is in the hunt. It means bigger than the pixel. So when the size of the pixel increases significantly, what happens to the resolution? Well, when this resolution is affected, essentially, you won't be able to perceive clearly all of those small objects present in that image. The pixel size must always be less than or equal to half of precisely the size of even just one smallest object in any given image. Taking into account every smallest piece within an image, contextually speaking, the pixel's actual measurable size must indeed remain smaller than, or at least equal directly relative towards being half-sized, compared against each individual tiny object found therein, which is absolutely essential if you wish truly ensuring production quality regarding good imagery results overall. If your specific chosen pixel sizes increase beyond these critical limits, then unfortunately,
the text explains that when the size of the object is smaller, the resolution of the images starts to decrease, which is what happened with C and D. There are small objects, but their pixel size is larger than the size of the object itself, so it cannot achieve discrimination or differentiate between one object and another in the image, resulting in what you see. The difference between A, B, C, and D is related to the matrix size or pixel size. When you increase or decrease the matrix size, you consequently increase or decrease the pixel size. For example, If you use a 32x32 matrix, the pixel size becomes larger than the size of the widgets present. In this case, you cannot see it or distinguish it, which is why this image appears as it does. The image in front of me looks like this, but why does the image on the right appear like that? The image is A. And C and D, why do these images look like this? If I take K and take Ampere and take all the factors the same in the four images, why do these images appear like this? The difference in these images is due to something that is also related to the pixel, not just the pixel size. This is related to something called the pixel. We all hear about the computer telling you that this image is a megabyte, right? But have you ever stopped to wonder what exactly a byte is, or even a bit? To understand this, the first thing you need to know is that when X-rays fall on any object, the detector translates the signal that falls on it, or the intensity that falls on it, into a signal. This process is quite fascinating because the detector is essentially converting the physical energy of the X-rays into an electrical signal that can be measured and analyzed. This signal, which is the complete wave, is called al-isharat al-tanadhuriyya. Al-isharat al-tanadhuriyya, or the analog signal, is crucial because it represents a continuous flow of information, unlike digital signals which are discrete. Okay, so the al-isharat al-tanadhuriyya that you see is continuous, meaning it can vary smoothly over a range of values, providing a more accurate representation of the original signal. It needs to be stored on the computer. So how is it stored on the computer? Will it be stored as kanalog, which is the Arabic term for analog, representing continuous signals? No, it needs to be converted to something called digital, or digital, which refers to discrete signals that computers can process. So how does this happen? I have my signal, which I call al-isharat al-tanadhuriyya, and the other one is musawid. So I input this signal into something called muhawwil al-isharat al-tanadhuriyya ila al-raqamiyya to convert the al-isharat al-tanadhuriyya you see into digital. This conversion process involves sampling the continuous signal at regular intervals and quantizing it into discrete values. Why do I convert it to digital? Because it will perform processing, image storage, and sending to the server. Digital form is essential because it allows for efficient processing, accurate storage, and reliable transmission over networks. Therefore, for processing and storage to occur, it must be in digital form. What is the digital form? The digital form, as you see, has a specific value, a single value, a value discrete value, which means it represents data in distinct steps or levels, while the al-isharat al-tanadhuriyya is a continuous wave with an infinite number of values, I perform something called al-ayna. What does al-ayna mean? It means I select a specific value, such as the amplitude peak of the wave I have, and then I start converting it from al-isharat al-tanadhuriyya to digital form. That's why during the conversion process from analog to digital form, there is a loss of data. So, what exactly is the relationship between this concept and images, you might wonder? Allow me to delve into this topic a bit further and provide a more comprehensive explanation. In the realm of digital technology, all data, including images, must be stored within a computer system. However, there's a fundamental challenge. Computers are inherently digital devices, which means they do not have the capability to understand or process analog values directly. Analog values, such as those you might encounter in everyday life, could be numbers like 0, 10, 15, or 20. These are continuous values that exist in the real world. Unfortunately, a computer cannot interpret these values in their natural form because it operates using a different system of understanding. Computers are designed to comprehend only the binary language, which is a system of numerical notation that uses only two symbols, 0 and 1. This binary system is the foundation of all computer operations and data processing. To effectively store and manipulate data, including images, within a computer, it is essential to convert these analog values into a format that the computer can understand. This process involves transforming the values from their original decimal form into binary form. In essence, your data must be represented in a series of zeros and ones, which is the binary system. This conversion is crucial because it allows the computer to accurately store, retrieve, and process the data as needed. By understanding this conversion process, we can better appreciate how digital images and other forms of data are managed within computer systems, ensuring that they are accessible and usable in the digital world. This data is digital data, referred to as binary. Both digital and binary are summarized in the term bit. Where is the bit, which represents 0 and 1? It is found within the pixel. What is it found in? Within the pixel. In digital imaging, each pixel of an image is composed of a certain number of bits. A bit is the most basic unit of data in computing and digital communications, representing a binary value of either 0 or 1. When we talk about 8 bits, we are referring to a byte, which is a standard unit of data that can represent a wide range of values. Now, when we say every 8 bits, or 1 byte, we are essentially asking how many different combinations or forms can be created with these 8 bits. The answer lies in the concept of powers of 2. Specifically, 2 raised to the power of 8, which is a mathematical way of calculating the total number of possible combinations. This calculation results in 256 different values, ranging from 0 to 255. Therefore, when we say 2 to the power of 8, we are talking about the ability to represent 256 distinct values, which is crucial in various computing processes, including image processing, where each pixel can have one of these 256 values, allowing for a wide range of color and intensity variations. So if I have 2 bits in the pixel, how many values can this pixel contain? 2x2 equals 4. So there are 4 values, only 4 values. Now if it has 3 bits, then 2x3 equals 8. What is 8? 8 values, meaning 8 shapes, or 8 configurations for this pixel. There are 8 configurations or 8 values, 8 shapes, or 8 values.
When discussing these specific pixels, let me break it down for you in simpler terms. In my image, each pixel is represented by just 1 bit. This means that each pixel is either on or off, black or white, with no shades of gray in between. So, what exactly does this single bit signify in the context of the image? It represents the most basic form of digital information, where each pixel can only be in one of 2 possible states, much like a binary switch.
It can be 0 and 1 or 1 and 1. So when I said I see the number of pizzas in my image, it means 2 and 1 in binary, which means 2 values. In binary representation, each digit represents a power of 2, which is crucial in computing. For example, when you see 2 pizzas, it translates to binary as 10, representing the number 2. This binary system is fundamental in digital technology, allowing computers to process and store data efficiently. 2 values in a pixel essentially indicate that your pixel can contain 2 values. The first value is 0, and the second value is 1. 0 represents the color white, and 1 represents the color black. This is the Han intensity of color that you are translating your signal into. So, when you have a pixel that contains 1 bit, your image will be a contrast between the color white and black, just like this digital image. In image number D, here you only see black or white. Are there any other colors? Are there any gray colors? Are there any grayscale colors? No, they are all black or white colors. Why is that? Because the resolutions available here are very, very, very limited and contain colors that mean 0 or white or black, or 0 or white or 1 or white. By increasing the resolutions available in this limited setting, what does that mean? It means you will provide more possible values or more potential variations within the pixel. In the second image here, which is number C, your pixel is represented by this square with the number of pixels it contains. Okay? So we choose here the pixel. Here you have 1 pixel, so you have the possibility of either 0 or 1. We said 2 raised to the power of, do you want to know how many values you can get? How many gray values, how many grayscale values? It's 2 raised to the number of pixels. So, if your number of pixels here is 1, then 2 raised to 1 equals 2. This means that each pixel can take on 2 values, either white or black in the grayscale, because 0 and 1 here increase the pixel a bit, right? It increases the pixel a bit. So consequently, your configuration or values will increase. For example, let's assume we increased it to 3 pixels, then 2 raised to 3 becomes 8. So the grayscale value that each pixel can take is 8. Therefore, there are 8 grayscale values. Initially, a pixel can be represented by 8 grayscale values. In this case, instead of just seeing black and white, you will see other colors available to you. The clarity increases and it becomes clearer. For example, if I set it to 4 pixels, then it would be 2 raised to 4. God willing, 16 value means that each pixel can take 16 values from the car grid. For example, if there is a pixel in the air, or a pixel in the bone, or a pixel in the weak area, you can represent it on a grayscale because you have flexibility, or you have values from gray values that you can use. You can store your information in many values or in configurations that are 16 value. Now, increase it. For example, you have the 255 gray values available for each pixel. So if there is a pixel, for example, with low intensity, it can represent medium intensity or high intensity. Therefore, you have 255 configurations or 255 values that each pixel can take, which affects the overall representation of the image. The image B, image C, and image D represent the number of pics present in each pixel. If your number of pics is reduced, you will eventually reach a minimum point, making it impossible to represent all the gray values in the image. The contrast is mentioned as you can see, but here you can only obtain a very limited number of gray values present in the image. I hope this explanation is clear and helps understand why the image appears this way. Thank you very much, and peace be upon you.